On Friday was about LC circuit. Today we will be mainly focusing on resonance, but I thought I will just quickly go over this one. So we have got a resistor, inductor, and a capacitor, all three in a circuit, and that's the alternating battery or supply voltage. Sometimes it's called generator voltage. So remember, the resistance of the resistor does not change even if the frequency of the supply is different. But an inductor and capacitor, their reactance depends on the frequency. So formula for the reactance of this one is 2 pi FL, and the formula to find the reactance of this one is 1 over 2 pi FC. So that means XC is inversely proportional to the frequency. It will have higher reactance at lower frequency and vice versa. This one is directly proportional to frequency, its reactance. So its reactance will be, if frequency is higher, it will have greater reactance. So depends on which one has got a higher reactance, because from these graphs you would have noticed, I'm not going to go into the detail, that current and voltage across the resistor, they're always in phase. Voltage across the inductor leads the current by 90 degrees. And the green one is the voltage across the capacitor. It lags the current by 90 degrees. And if you look at the VL and VC, they have got opposite phase, so they cancel each other's effect. So similarly, because why the voltages have got opposite phase? Because XL and XC also have got opposite phase. So if we look at this kind of what we call as vector or phases. So generally VL or VC is represented here, and VR is over here. And similarly, XL, that's the reactance of the inductor, capacitor, they're shown over here, and resistance of that one is over here. So if XL is larger than XC, so it will be an inductive circuit. That means it will behave like as if it was inductor only in the circuit and capacitor wasn't there. If, however, this one was larger than that one, as is shown in the diagram here, so this is the voltage graph, which are exactly similar to the reactance graph. So if this one is larger than that XL, then this one becomes a capacitive circuit. And that's the total impedance. So in resonance, what we will look at, because by changing the frequency of the supply, reactance of this one and reactance of that one changes. So in resonance, we see what happens when XL and XC are exactly equal. So if I could bring my other set of notes. Okay. So now, if you look over here, so if we increase the frequency or decrease the frequency in such a way that XL and XC, they are exactly equal, so they cancel each other. And when they cancel each other, the total impedance in the circuit will be equal to R. And that is the minimum one, because if you looked over here in the previous one, so that is the total impedance of XL, XC, and R together, and it's always more than R. Or so that was an inductive circuit. In a capacitive circuit, this set, which is the total impedance of all three together, it is larger than R. Okay, so if impedance is larger, that means current in the circuit will not be at its maximum value. By looking at, so what happens, what do we mean by resonance? Resonance is the frequency of the supply is such that XL and XC, they become equal. And when they become equal, the total impedance in the circuit becomes minimum. And how much is the minimum impedance? That is equal to R. And if R is minimum, that means at this particular frequency, current will be maximum in the circuit. And so current will be equal to, that is the supply voltage, that's the total impedance, because at resonance, Z impedance is equal to R. So we can either use that one or that one because Z and R are the same. So that will give you the maximum value of current. Now, another thing, and this particular frequency, when XL and XC become exactly equal, that is called the resonant frequency. And so what happens at resonance is XL is equal to XC. Those are equal and opposite as you looked up here. Total impedance is minimum, and that is equal to R. VL is equal to VC, and current is equal to supply voltage over R. Now, the graph, if we change the frequency, then remember the formula for XL is 2 pi FL. That means XL is directly proportional to F. By increasing this one will increase. But if we increase F, then XC will decrease. It's inversely proportional. So XC will be greater at lower frequencies. 1 divided by something smaller will be a larger value. So if we look at this graph over here, so at lower frequency, LCR circuit will behave like a capacitive circuit because XC will be larger. Therefore, current will not be very large. Current will be small. Whereas higher frequency, it will behave like an inductive circuit. So therefore, inductive circuit, that means total impedance is larger and current will be not that large. But at that particular frequency, when XL and XC are exactly equal, that is called the resonant frequency. Now, in this formula, so if we want to calculate the resonant frequency, we have to make XL is equal to XC. You use these formulas and you come up with this formula. But that formula is not given in the test or at the exam. So you have to remember that XL is equal to XC and then do all these changes and then calculate the frequency from these formulas over here. These formulas are given, but not this one. I want to show you, is everyone following so far?
Yeah.
Yes.
Okay.
Yeah.
That's fine. Okay. So I want to show you an animation, and which looks a bit complicated, but if we go step by step, it wouldn't look as complicated. So what we have got over here is, this is a resistor, this is a capacitor, there's an inductor, and then we have AC supply there, and we can change frequency, we can change all different things. So at present, if you look over here, resistance of the resistance, they haven't given this one. Okay, so sorry, the voltage. So voltage across the capacitor is 9.3 volts, and voltage across the inductor is 3.7, and voltage across the resistor is this much. If you look over here, so resistance is about, I think, 1.6 ohm. XC is 15.5 and XL is 6.2. So at this stage, is it a capacitive circuit or inductive circuit? Capacitive circuit. So total impedance is already given here. So if we look at this graph over here, so at this particular frequency, which is the frequency somewhere about 19.7 hertz, it is a capacitive circuit, and these ones are giving you, these graphs are giving you the actual values at different times where the dot is at that particular instant. That is the value of the voltages. So you can see from the amplitude that VC is larger than VL, and VR is even smaller, okay, than any of these one. So let's see if I increase the frequency, what happens to these voltages, or you can see over here. We can't see all three things, but you can play on your own in your own time. But let's just look at the voltages, what happens to the voltages. And this one over here is showing us the current. So presently current is 0.6 amps. So we will just focus maybe at this one. So I will increase the frequency. So as I'm increasing the frequency, current in this one has increased. And why the current has increased is because this one has VL has increased and this one has decreased, so they're becoming closer and closer. So current has increased. So this one, on this side we've got current, and on this side we've got frequency. So let's make it a little bit more. Okay, so somewhere over here, somewhere over here, if I do it at resonance, somewhere over here, as you can see, that current is maximum 3.5 amps. And you can see that these two values, VL and V voltage across the capacitor, they're exactly equal, because over here XC and XL are equal, and therefore at this stage current is maximum. Before that, at lower frequency, current was somewhere this much value, or it was this much value. Now these one over here, so the blue one is the voltage across the, these are the phasors. So blue one is the voltage across the capacitor, the green one is the voltage across the inductor, and the little red one is the voltage across the resistor. Let's increase frequency even higher. So if I increase it higher, circuit is not at resonance anymore because current has decreased from 3.5 to 7.9. So now it has become an inductive circuit. And if I keep increasing it, it will become more and more inductive. Okay, so let's say, any questions, girls, about this animation? There's a lot in this one. So there are a lot of variables that we can change. So say, for example, I set the current at resonance, and then we increase the capacitance of the capacitor. So capacitance is presently 52 ohm. So if I increase the capacitance, so it has now become an, has it become an inductive circuit or a capacitive circuit?
Capacitive. I mean, inductive.
Inductive circuit. So if I want to bring it back to the resonance, what can I do to the frequency to bring it back to the resonance? Do I need to increase the frequency or decrease the frequency? Because now XL is more. You can see that XL is more than XC. So we need to decrease it. So we need to decrease the frequency. So, okay, so we now need to decrease the frequency, and by decreasing the frequency, it has reached the resonance again. So you can play with these different things, but overall, what we are saying is that resonance happens when XL and XC, they're exactly equal in size. Presently, they're not equal. I will just make it exactly equal. Then XCL, XL, they're exactly equal. And because they're exactly equal, impedance, total impedance is minimum, and that is equal to just R, that you can see from here, 1.6 and 1.6. And because total impedance of all these three is minimum, current in the circuit is maximum. And the graph shows like this one. So lower frequency, it behaves like a capacitive circuit. Somewhere over here is resonance, and at higher frequency, it behaves like an inductive circuit. So it's similar to the resonance in when we were doing mechanics. We will, we had those different kind of strings, and there are different objects which were hanging, and we were moving it. And there was a driving pendulum, and the string that was moving with the largest amplitude was the one which had the same length as the driving pendulum. So in mechanics, if something moves with the largest amplitude, like when the earthquake comes, so the building which move with the largest amplitude, the one which move back and forth maximum, their frequency matches with the frequency of the earthquake. And those buildings are most likely to fall in the case of an earthquake, whereas other buildings, they might be taller, but if their frequency, the natural frequency doesn't match with the driving frequency, they don't fall. So it's a similar concept over here. So in electrical resonance, current becomes maximum because the total impedance becomes minimum. So that was about this one. And so if I could just, let me see where, stop sharing. Okay, we are back onto the main screen. So any questions about today's notes or the demo? That demo was there to explain it to you, you know, how the resonance works, give you some kind of a picture in your head that what do we mean by the resonance in LCR circuits. So all the notes and kind of demo that they were all good?
Yeah.
Yeah. Okay, that's good. So there's one more lesson, which is tomorrow's lesson, and that is if there is only a capacitor and inductor in a circuit, and in that lesson it is about electromagnetic oscillation. So capacitor is charged and then it is discharged through an inductor. But I think we can just only do a few things at a time, so I wouldn't go into the detail of that one. So that is just a short lesson. And then your assignment is due on Thursday, assignment on this AC, and that will be the end of this topic. And then we will start some revision. So if you want to do any particular kind of, so there are three things, you know, like electricity, mechanics, and waves. So those are the three topics. So either you send me your choice, which one you want to revise first. So if you give me some indication, I don't want the indication now, but you can send me an email, or we will have time to revise all three topics. So it doesn't matter which one we decide first or which revise first and which one we do later. But that's what we will be doing from between now until the school opens. So any other question? Okay, it's good to see Cherry. Hi, Cherry. Hi, Angelique. I didn't see Olivia is there. Hi, Olivia.
Hello.
How are you? How are you guys today?